Math 2414, Calculus 2, Calculus 1 review, Integration by Substitution, Examples, Part 1. On the board I have a couple of integrals, one indefinite, one definite. Do not let these square roots intimidate you. Number one, they're just square roots, and number two, they're chosen for a reason. You'll see why in a moment. All right, but let's start with this one, the integral of tangent of x dx. Now, 2 videos ago, I gave you a list of integration rules, and this was one of them. And I'd mentioned in there that this one was not just simply whose derivative is tangent, because no obvious function has a derivative of tangent, but that in order to find its antiderivative, we would have to use substitution. Well, now's a good time. So if you ever forget the integral of tangent, here's how you rediscover it. The trick to finding the integral of tangent is to rewrite it as the integral of sine over cosine. Which makes the problem look worse. But in the context of substitution, here's why it actually got better. The whole premise behind substitution is to try to match an integral to another one that kind of has the same form. And when we had our integral rules, which I have in front of me right now, there were 3 of them that were the integrals of fractions. If you had them written down, they were numbers 2, 15, and 16. Now 15 had u squared plus a squared on the bottom, and there's no sum down here, so forget that. And then 16 had a square root of a subtraction problem, and that's not even there. But number 2, integral rule number 2, was the integral of 1 over u du is equal to the natural log of the absolute value of u. And structurally, this integral is a fraction like this one. Now, it doesn't have a 1 on the top, and it doesn't have a u on the bottom, but the whole purpose of substitution is to try to fix that thing. So if we decided to try to use substitution to transform this integral into this rule, then the u on the bottom is telling me where my substitution is. So let's try that. And by the way, don't ever be afraid to try a substitution, because one of 2 things will happen. It will work or it will crash and burn. But if it crashes and burns, that's okay. It's a learning process. You see why it didn't work, and then you're a little more analytical when you choose your substitutions in the future. But for this one, we're going to let u equal the denominator cosine of x in an effort to convert the integral to this rule. So if u is equal to cosine, then what is du? Well, the derivative of cosine is negative sine. So du is negative sine x dx, and if we solve for dx, then we would divide both sides by negative sine. So dx would be du over negative sine x. So the cosine is going to become u, and du is going to become negative sine x. Excuse me, dx is going to become du over negative sine x. So let's see what happens. Now, when you are making all these substitutions, stay very focused on taking inventory of what's changing and what's not changing. For example, this cosine of x is going to become u. That was by my own choice. This dx is going to become du over negative sine of x. But which piece of this integral have we not accounted for yet? And the answer is this sine of x. So in all these substitutions, that sine of x is currently still there, which normally would be a bad thing, because when we're changing it, we need to change completely from x's to u's, and we still got this x lurking here, but guess what? There's another sine x down here. These sine x's cancel. They're both parts of multiplication problems. Be careful, the negative does not cancel. So I'm going to take that negative and pull it out in front of the integral. Everything in the numerator canceled, leaving a 1. The only surviving denominator is the u. We have the du. And voila, we've successfully converted it to this rule. We saw the negative in front. The integral of 1 over u is the natural log of the absolute value of u. Don't forget the plus c. And then the u is holding the place for cosine of x. And it looks like we have an answer. Now you might be thinking, but that's not what was in the integration rules. I know, but when I wrote it down, I mentioned that there was an equivalent version, and this is it. I'll show you why it's the same as the rule that we had listed a few videos ago. But in terms of substitution, the trick for integrating tangent is to rewrite it as sine over cosine, and then let u equal cosine so that we can set up this integral rule. If you tried u equals to sine, you would find out that it would not work because not all the x's would disappear like they did here. Now, before we move on to part B, I want to quickly show you why this is the same as the answer as before. It involves a little bit of algebra, a little bit of trigonometry, but not too much of each. In fact, I'm not even going to worry about the plus c. That's not the part I'm trying to fix. Number one, a negative in front is like multiplying by -1. Okay? Number two, there's a logarithmic property that says if you have a number in front of a logarithm, you can move it inside as an exponent. So we can move the -1 inside as an exponent on the cosine. Now be careful, that's not cosine inverse, that's cosine of the -1. This is why I don't like using this for inverse trig functions, because it could be a power. Speaking of it as a power, to raise something to a -1 power means to take its reciprocal. So we get the absolute value of the reciprocal of cosine of x inside the logarithm, and we have a trig identity that says 1 over cosine is secant. So if we go to stick the plus c back on, it would turn into the rule that was in the integration table, or the integration rules. All right, so that's how you recover the antiderivative of tangent if you've forgotten how to do it. Rewrite it as sine over cosine, do a substitution of u equals cosine, and then chase it down. And you can do the same thing for the integral of cotangent. You would have, instead of sine over cosine, you would have cosine over sine. You would let u equal sine, and it would get the job done. All right, let's focus on this guy. Do not worry about the limits of integration yet. We'll talk about those when the time is right. Let's focus on the integrand. We don't have a rule that starts with the square root, but we have a rule for powers. And when we took the derivative of a square root in the previous video, we started by rewriting it as a power. So I'm going to say now what I said then. Don't do calculus to radicals. Do calculus to powers. See a radical, make a power out of it. So let's start by not doing any calculus, but simply rewriting the square root as 1/2 power. Now, which rule are we going to try to connect this to? Well, it's got a power, so maybe we should try to connect it to the integral of u to the n du is equal to 1 over n times u to the n plus 1 plus c. All right, if we're going to go down that path, then who's going to be the u? The guy with the power, that would be the 1 plus x squared. So we're going to let u equal 1 plus x squared. Okay? Let's play the du game. Then du equals the derivative of this, which is 2x times dx. So dx, if I divide both sides by 2x, is going to be 1 over 2x times du, or du over 2x, whichever one works for you. But there's another issue here that's a little stealthy, but very important. And in Calculus 3, when you have double and triple integrals, you have to stay laser focused on your limits of integration and what variables they are values for. These limits of integration are values for this variable, for x. It would not be wrong to say x equals on both of these limits of integration. It would just kind of be redundant, because what else could they equal in this single integral? Again, in Calculus 3, by the way, Calculus 3, you really don't learn many new techniques. You just A, talk about vectors, and B, start doing calculus in multiple dimensions. But it's not like you learn a whole slew of new integration rules or anything. So why am I bringing this up? Because right now I'm trying to transform this from x's to u's in an effort to match this integration rule. But these aren't the only x's floating around, so are these. When you do substitution on a definite integral, you have to be very careful with the limits of integration. And there's two things that you can do. One is let them sit there until the very end and then stick them in. And that's not wrong. But the problem with waiting until the very end is that if you forget to undo the substitution and then substitute your limits of integration, you'll miss it every time. For example, let's pretend we had numbers here. If I put them in for u, that's a mistake because they would represent x values, not u values. So method number one for doing a definite integral using substitution is to hold on to the limits of integration until the very end. But method number two, and I think it's a little more slick, and you'll see why at the end, is to change the limits of integration. Now what do I mean by that? Well, let's start with the bottom limit of the integration. If x is equal to the square root of 3, then what will u equal? Well, u is defined to be 1 plus x squared. So u would be 1 plus the square root of 3 squared, which I got by simply substituting the square root of 3 for x into this substitution equation. Well, the square root cancels the square, that leaves 1 plus 3, so I get u equals 4. And for the for the upper limit of integration, I meant to do that one first. If x equals 2 times the square root of 2, then what does u equal? Well, let me substitute 2 times the square root of 2 for x in my substitution. This one you have to be a little bit more careful because you're squaring two things. 2 squared is 4. The square root of 2 squared is 2. So we get 4 times 2 is 8. 8 plus 1 is 9. That means when I make the substitution from x's to u's, I can change not only this and the dx, but I can change the limits of integration as well. So, let's take inventory of everything that's going to change. This 1 plus x squared is going to become a u. So we have u there. This dx is going to become 1 over 2x times du. This square root of 3 as an x value converts to a value of 4 for u. And this 2 square root of 2 as an x value converts to a u value of 9. And you have to forgive me, I meant to write these things in green. Give me 1 second to change all that. All right, so again, take an inventory. The square root of 3 for x became 4 for u. The 2 square root of 2 for x became 9 for u. The 1 plus x squared became u. That was our original substitution. And the dx became 1 over 2x du. So who's not accounted for? Who did I not circle? This 2x, this 1/2. I'll be honest, when you're doing substitutions, you should go a lot more fluidly than this. And really, I'm doing more of a Calculus 1 lesson than a Calculus 2 lesson, but I know substitution's not going away, so I think it's worth the time. All right, let's see where we are. Well, the 2x is canceled, that's good. And let's clean this mess up. We have the integral from 4 to 9. Remember, those are u values of u to the 1/2 du. And now I've etched this rule. And so I just have to play it out now. The rule says add 1 to the power. 1/2 plus 1 is 3/2. And then multiply by the reciprocal of that power in front. But if your power is a fraction, its reciprocal is just turning it upside down. In other words, 1 over 3/2 is 2/3. And by the way, you can check that derivative real fast. Bring the power down, multiply, everything cancels, and it gets lower to 1/2. No plus c because it's not a definite integral. Excuse me, it's not an indefinite integral. And we're evaluating this from 4 to 9. Now, here's the advantage to changing the limits of integration at the beginning. If I had kept these, they would have been x values, but this is u. And you might incorrectly substitute them at that point. If you kept the x values, if you kept the square root of 3 and the 2 square root of 2, then you would have to change this back to an x. So, here's the advantage to doing this move. If you change the limits of integration, which we did, comma, you do not have to undo the substitution after you find the antiderivative. A lot of words there. if you change the limits of integration like we did here, you do not have to undo the substitution after you find the antiderivative. These are u values, that's a u. Again, and I'm going to put these back. Had these stayed 2 square root of 2 and square root of 3, you might incorrectly substitute them in right now, which would be bad because they're not u values. You would have to go to the next line, change the u back to 1 plus x squared to 3 halves, and then from square root of 3 to 2 square root of 2, and now you would substitute them into 1 plus x squared like we did at the beginning. So really all you're doing is, instead of waiting until the end to put the limits of integration, you're doing it at the beginning and getting it over with now, which eliminates the need to undo the substitution. So it's not extra work to substitute those numbers in, you're just doing it sooner than later to remove one extra move at the end. All right, so let's substitute. Let's put this back where it was, which was 4 to 9. All right, so if we substitute the limits of integration, we get 2/3 times 9 to the 3 halves minus 2/3 times 4 to the 3 halves. And I would expect you to simplify that. I'm not going to do an arithmetic review on rational exponents, but I will remind you that a denominator tells you the root and the numerator tells you the power. So 9 to the 3 halves means square root and third power. The square root of 9 is 3. 3 to the third power is 27. The square root of 4 is 2. 2 to the third power is 8. I think I'm going to factor a 2/3 out of this so that we can just do 27 minus 8. 27 minus 8 is 19. And now I can just multiply these together. 2 times 19 is 38. 38 thirds. And finally, the problem ends. I think this video went longer than I wanted. Yeah, it did. But I knew that second example I had a lot to say. We'll do one more video, a couple more examples.